our start point for doing calculations with integrals is going to be with double integrals. So double integrals are going to tell us the volume that's enclosed under a graph in the same way that single integrals told us about area under a graph. So if we've got some function f of x, y of two variables, we can draw its graph by setting z equal to f of x, y, and that gives us some kind of sloping surface. And if we want to know the volume that's trapped between that surface and the xy plane, this flat area down here, we can calculate a so-called double integral, and we write it like this. It's the double integral of f of xy dA, and dA means kind of with respect to area, and it's just kind of a shorthand. There's one thing that is also in the notation here. Here I've written the double integral over R, and that indicates that we also have to specify, we don't just want all of the area under this graph. There's some certain region downstairs in the xy plane, and we just want the volume that's trapped directly over top of it, the stuff that we get by looking at all those parts that are directly between the xy plane and the graph over this region. So double integrals, as I said, they're like single variable integrals, and we calculate them, or we define them in kind of the same way. When we were doing single variable integration, what we did was we took our graph here and we divided up our region that was underneath it into little tiny spaces. Over each of those spaces, we saw how high the graph was, say at one end, and that gave us a little rectangle. And we did that for all of those little areas over there. And then we calculated the total area of those rectangles and added them up. And then we just keep doing that, but let the little size that we're dividing up into get smaller and smaller, and took a limit. So that's the so-called Riemann integral when we are doing functions of single variable. For functions of two variables, it's very, very similar, except now we're dividing, say, a rectangular region in the xy plane into progressively smaller and smaller rectangular subdivisions. And then we are multiplying the area of those little rectangles by the volume of the region we see over top of it, and calculating the total volume contribution. And we have to keep track of this fact that I mentioned in the previous video, that area below the axis, or area below the xy plane, counts as negative area or negative volume. Now, one of the things that's going to be more complicated is the region of integration. And I cannot stress this enough. I'm going to stress it a lot, but I don't think I can stress it enough. This is going to be troublesome for the majority of the course. Now, when we're talking about single variable integrals, there's not a lot of things we can do. If we want to integrate a graph over top of some region, that region could maybe be a little interval. There's not a lot of one-dimensional shapes that live inside one-dimensional space. But if we're talking about a two-dimensional shape inside the xy plane, we can have rectangles, circles, triangles, any manner of region inside two-dimensional space is something that we could take the double integral over for. So our region R could be any of these types of shapes, and we have to account for that when we're doing the integration. That's the main thing to be aware of, and it's also a little bit more complicated, but because we're going to calculate double integrals by doing an ordinary integral twice in a row, and we'll see how that goes. So here's an example. Let's say we've got this region R. It's the region of all those points inside the xy plane where x is between 0 and 1, and y is between 2 and 3. So it's a little, in fact, a square region up here. If we want to calculate the double integral of this function, x times y, with respect to area, we do an integral from 0 to 1 and an integral from 2 to 3 of x times y dy dx. So the first thing is that these integrals are like parentheses. We work from inside to out. So the first thing we should do when we do this integral is calculate the integral on the inside. So we do the integral from 0 to 1, and just like with partial derivatives, when we integrate with respect to y, we leave x alone. We treat it as a constant. So an antiderivative of x times y with respect to y is just x times y squared over 2. We just find that, and then we evaluate it between y equals 2 and y equals 3. And then that becomes the integral from 0 to 1, the integral of this between y equals 2 and y equals 3. Well, that's going to be x times 9 over 2 minus x times 4 over 2, like so. And that's kind of it. We can simplify it a little. It becomes the integral from 0 to 1 of 5 over 2x dx. That finishes solving the inside integral, and now we move one stage out and we calculate the integral on the outside. This is the integral from 0 to 1 of 5/2 x, so we find an antiderivative, which is 5/4 x squared. We're going to evaluate that between 0 and 1, so that's 5/4 times 1 minus 5/4 times 0, and so the whole thing is 5 over 4. So mechanically, it's the same as doing single variable integrals, just twice in a row, working inside to out. And we treat the variables we haven't encountered yet as constants when we're doing the variables on the inside.